Now let's consider a little more detail about how ions form in solution. In particular, let's look at how people talk about the energy of formation of ions in solution. We had mentioned when we talked about entropy of formation, even though entropy, you can define absolute entropy at 0 Kelvin of a perfect crystal to be 0. Let's actually just go back and look at those standard enthalpies, free energies, entropy standard. So here's the standard entropies of formation. You start at 0 Kelvin, you go to 298, make various corrections for phase transitions and so on. So we expect, since they're starting at 0 and can get only positive numbers, that we would expect that we'd always get positive numbers for those. But what you find is that sometimes, oh look, negative numbers. You get negative numbers for entropy of formation of ions. Here's ion, that's a positive number, but sometimes you get negative numbers. Okay, here's a magnesium, negative. And why was that? Well, we said that the convention is we'll define everything, the standard enthalpy of formation, the standard entropy of formation, the standard free energy of formation of H plus to be 0. So that's what we're defining to be 0. So that's why you get negative numbers. So sometimes the entropy, for instance here, of iron 3 plus is negative with respect to hydrogen. We also, for electrochemical reactions, remember, for the reduction, we had half reactions and reduction half reactions. We said that we're going to have this reduction half reaction. We're going to define that with standard conditions to be 0. So if we look at standard electrode potentials, E0, this is a table for standard reduction potentials, and we have, not arbitrarily, but by convention, set the standard reduction potential for hydrogen to be 0. And as we said, the standard free energy, enthalpy, and entropy of ions are all measured with respect to H plus aqueous, which we're defining to be 0. So how do you actually figure out, or how would you actually calculate the free energy formation of ions? Well, typically what you do is you take the solvent, and for simple theories, you take the solvent as a continuum, and then you ask how much energy does it take to make a cavity in that solvent, and then how much energy do you get when you put in a charged species? And that, of course, depends on the solvent and so on. Another way to look at that is through this thermodynamic cycle. Here's the solid, and what we're going to do is to break apart the solid into ions and solvate them. In this particular case, we're looking at solvation by water, aqueous solutions. So that's step one. Well, as we've done in the past, we can do a thermodynamic cycle. So here we take the solid and break it apart in order to form the ions in the gas phase. Now we have the ions in the gas phase. We're going to put them, in this case, water, and see how much energy is, in this case, would be a favorable energy, so energy will be released. So this first part depends upon lattice energy, ionization energy, electron affinities, and so on. And then this step here is the hydration energy. That step is directly related to how much energy it takes to form the ions in a solution. And as we said, we're going to talk in the next section of this lecture about the Debye-Huckel theory, and essentially that's what you do is you try to make a cavity in a solvent and then stick the ion in that cavity.